Article 630.11b of the National Electrical Code addresses the calculation of non-continuous loads for welding equipment. This article is particularly relevant when designing electrical systems for facilities with multiple welding stations, such as the school welding training area. The core principle is that not all welding machines will operate at their maximum rated input simultaneously. Therefore, the code allows for a demand factor to be applied, reducing the overall calculated load. The calculation method outlined in Article 630.11b involves applying different percentages to the input current of individual welding machines based on their size and quantity. This approach allows for a more realistic estimation of the total load compared to simply summing the maximum input current of all welding machines. Article 630.11b uses a tiered percentage reduction based on the ranking of the welding machine's input current. This tiered approach is in line with electrical engineering practices for dealing with a quantity of non-coincident loads. Let's look at the specific calculation in the example. The problem states that each welder has an input of 45.5 amps. The task is to determine the non-continuous load for 10 welding stations, assuming all 10 may be in use simultaneously. According to Article 630.11b, the calculation proceeds as follows. Firstly, calculate 100% of the two largest welders. Secondly, calculate 85% of the third largest welder. Thirdly, calculate 70% of the fourth largest welder. Finally, calculate 60% of all remaining welders. In this example, since all welders have the same input current, the two largest welders are 45.5 amps each. So, 100% of the two largest welders is 45.5 amps multiplied by 2, which equals 91 amps. The third largest welder is also 45.5 amps. Therefore, 85% of the third largest welder is 45.5 amps multiplied by 0.85, which equals 38.7 amps. The fourth largest welder again is 45.5 amps. Hence, 70% of the fourth largest welder is 45.5 amps multiplied by 0.70, resulting in 31.9 amps. The remaining 6 welders also have an input current of 45.5 amps each. Thus, 60% of the remaining 6 welders is 45.5 amps multiplied by 0.60 multiplied by 6, equaling 163.8 amps. To determine the total non-continuous load, sum all the calculated values. This involves adding 91 amps, 38.7 amps, 31.9 amps, and 163.8 amps. The total is 325.4 amps. Therefore, the non-continuous load for the 10 welding stations, as calculated using Article 630.11b of the NEC, is 325.4 amps. This value is the basis for determining the appropriate size of conductors, overcurrent protection devices, and other components of the electrical system. When applying Article 630.11b, it is crucial to accurately determine the input current of each welding machine. The input current is typically found on the nameplate of the welding machine. The nameplate provides critical information such as voltage, amperage, and duty cycle. The duty cycle is the percentage of time during a 10-minute period that the welding machine can operate at its rated output without overheating. This information is essential for determining the appropriate conductor size and overcurrent protection for the welding circuit. It is also crucial to consider the specific type of welding machines being used. Different types of welding machines, such as arc welders, resistance welders, and gas tungsten arc welders, have different input current characteristics. The NEC provides specific rules for each type of welding machine. For example, Article 630.31 addresses the supply conductors for motor generator arc welders. Article 630.21 addresses the supply conductors for resistance welders. The installation of welding equipment must comply with all applicable requirements of the NEC, including those related to grounding, bonding, and overcurrent protection. Grounding is a process of connecting non-current carrying metal parts of the electrical system to earth. Bonding is the process of connecting different metal parts of the electrical system together to create a low-impedance path for fault current. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect the electrical system from overloads and short circuits. It is important to select overcurrent protection devices with the appropriate interrupting rating for the available fault current at the point of installation. The available fault current is the maximum current that can flow in the short circuit. This value is determined by the utility company and can be obtained from the electrical engineer who designed the building's electrical system. In addition to the NEC, other codes and standards may apply to the installation of welding equipment. These may include local building codes, fire codes, and occupational safety and health administration regulations. It is important to consult with the local authorities and the facility's safety officer to ensure compliance with all applicable requirements. Proper ventilation is essential in welding areas to remove fumes and gases produced during the welding process. Welding fumes can contain hazardous substances such as metal oxides, fluorides, and ozone. These substances can cause respiratory problems and other health issues. The ventilation system should be designed to capture fumes at the source and exhaust them to the outside. The system should also provide adequate air changes to maintain a safe and healthy work environment. The design and installation of ventilation systems for welding areas is typically governed by industrial ventilation standards such as those published by the American Conference of Governmental Industrial Hygienists. These standards provide guidance on the selection of appropriate ventilation equipment, the design of exhaust hoods, and the calculation of airflow rates. Proper lighting is also important in welding areas to provide adequate visibility for welders. Poor lighting can cause eye strain, fatigue, and errors. The lighting system should be designed to provide uniform illumination throughout the welding area. The lighting fixture should be located to minimize glare and shadows. The selection of appropriate lighting fixture should also consider the color rendering index, which is a measure of how accurately the light source renders colors. A high color rendering index is important for welding applications to allow welders to accurately distinguish between different metals and welding consumables. Regular maintenance of welding equipment is essential to ensure safe and reliable operation. Welding machines should be inspected regularly for damage, wear, and loose connections. Welding cables should be inspected for cuts, abrasions, and other damage. Welding electrodes and other consumables should be stored in a dry place to prevent contamination. All electrical connections should be checked and tightened periodically. The ventilation system should be inspected and cleaned regularly to ensure proper airflow. A lighting system should be inspected and maintained to ensure adequate illumination. It is crucial to keep a record of all inspections and maintenance activities. This record should include the date of the inspection, the findings, and any corrective actions taken. This record can be used to track the performance of the welding equipment and to identify potential problems before they become serious. Safety training is essential for all welders and other personnel working in welding areas. The training should cover topics such as electrical safety, fire safety, and the hazards of welding fumes. Welders should be trained on the proper use of personal protective equipment such as welding helmets, gloves, and respirators. They should also be trained on the proper procedures for operating welding equipment and for handling welding materials. The training should be provided by qualified instructors and should be updated regularly to reflect changes in technology and regulations. Article 630 in the NEC covers electric welders and provides requirements for the installation of electric welding equipment. It addresses the sizing of conductors, overcurrent protection, disconnecting means, and other aspects of the electrical system that supply welding equipment. The specific requirements vary depending on the type and size of the welding equipment, as well as the duty cycle of the welding operation. Proper application of Article 630 is essential to ensure the safe and reliable operation of welding equipment and to protect personnel from electrical hazards. In addition to the specific requirements for welding equipment, the general requirements of the NEC also apply. These include requirements for grounding, bonding, wiring methods, and overcurrent protection. It is important to be familiar with all applicable requirements of the NEC when installing welding equipment. The non-continuous load calculation provides a basis for determining the minimum size of conductors that supply the welding equipment. The conductor size must be sufficient to carry the calculated load without overheating. The NEC provides tables that specify the ampacity of conductors based on their size, insulation type, and installation conditions. The overcurrent protection device protects the conductors from overloads and short circuits. The size of the overcurrent protection device must be coordinated with the ampacity of the conductors. The NEC provides rules for selecting the appropriate size of overcurrent protection device. A disconnecting means is required to isolate the welding equipment from the electrical supply for maintenance or repair. The disconnecting means must be readily accessible and capable of being locked in the open position. The NEC provides requirements for the type and location of the disconnecting means. Grounding is essential to protect personnel from electrical shock hazards. The welding equipment and the electrical system that supplies it must be properly grounded. The NEC provides requirements for grounding electrodes, grounding conductors, and bonding connections. Bonding is required to connect all non-current carrying metal parts of the electrical system together. This creates a low impedance path for fault current and helps to prevent electrical shock hazards. The NEC provides requirements for bonding conductors and bonding methods. Wiring methods must comply with the requirements of the NEC. The wiring method must be suitable for the environment in which it is installed. The NEC provides requirements for different types of wiring methods, such as conduit, cable, and wireway. The design and installation of electrical systems for welding equipment should be performed by qualified electrical professionals. These professionals should be familiar with the NEC and other applicable codes and standards. They should also have experience in the design and installation of electrical systems for industrial applications. Welding machine manufacturers also provide valuable information about the installation and operation of their equipment. This information should be consulted before installing or operating any welding equipment. Manufacturers' instructions typically include details about the electrical requirements of the equipment, as well as safety precautions that should be followed. Ignoring manufacturers' instructions can lead to equipment damage, personal injury, or even death. The example discussed focuses on a scenario where all welding machines have the same input current. In situations where different welding machines have different input currents, the calculation according to Article 630.11b requires careful consideration of the individual load characteristics of each machine. First step is to rank the welding machines in descending order based on their input current. The welding machine with the highest input current is considered the largest, the machine with the second highest input current is the second largest, and so on. The 100% factor is applied to the largest welding machine, the 85% factor is applied to the second largest welding machine, the 70% factor is applied to the third largest welding machine, and the 60% factor is applied to all remaining welding machines. This tiered approach ensures that the larger welding machines, which are more likely to be used at their full capacity, are given a higher weighting in the calculation. For example, consider a welding shop with 5 welding machines with the following input currents. Welder 1 is rated at 50 amps, Welder 2 is rated at 45 amps, Welder 3 is rated at 40 amps, Welder 4 is rated at 35 amps, and Welder 5 is rated at 30 amps. Following the steps outlined in Article 630.11b, the non-continuous load is calculated as follows: 100% of the largest welder is 100% of 50 amps equals 50 amps. 85% of the second largest welder is 85% of 45 amps equals 38.25 amps. 70% of the third largest welder is 70% of 40 amps equals 28 amps. 60% of the remaining two welders is 60% of 35 amps plus 60% of 30 amps, which equals 21 amps plus 18 amps equals 39 amps. The total non-continuous load is 50 amps plus 38.25 amps plus 28 amps plus 39 amps, which equals 155.25 amps. Therefore, the non-continuous load for the welding shop is 155.25 25 amps. This value is used to determine the appropriate size of conductors, overcurrent protection devices, and other components of the electrical system. In addition to considering the input current of each welding machine, it is also important to consider the duty cycle of each machine. The duty cycle is the percentage of time during a 10-minute period that the welding machine can operate at its rated output without overheating. Welding machines with high duty cycles are more likely to be used at their full capacity for longer periods of time. The NEC allows for adjustments to be made to the non-continuous load calculation based on the duty cycle of the welding machines. For example, if a welding machine has a duty cycle of 60%, the calculated load can be multiplied by 0.60 to account for the fact that the machine will not be operating at its full capacity for the entire time. It is important to carefully consider the duty cycle of each welding machine when calculating the non-continuous load. The duty cycle information is typically found on the nameplate of the welding machine. In some cases, it may be necessary to consult with the welding machine manufacturer to obtain accurate duty cycle information. The NEC also provides rules for calculating the load for resistance welders. Resistance welders are typically used for high-volume production welding applications. They are characterized by high input currents and short duty cycles. The NEC provides specific rules for sizing the conductors and overcurrent protection devices for resistance welders. These rules take into account the unique characteristics of resistance welding equipment. Article 630.31 of the NEC addresses the supply conductors for motor generator arc welders. Motor generator arc welders use a motor to drive a generator that produces the welding current. These types of welders are typically used for large-scale welding operations. The NEC provides specific rules for sizing the conductors that supply motor generator arc welders. These rules take into account the motor starting current and the generator output current. It is important to consult Article 630.31 when designing the electrical system for motor generator arc welders. The NEC is a complex and comprehensive document. It is essential to have a thorough understanding of the NEC when designing and installing electrical systems for welding equipment. It is also important to stay up to date on the latest changes to the NEC. The NEC is revised every 3 years, and it is important to be aware of any changes that may affect the design and installation of welding equipment. Continuing education courses and professional development programs are available to help electrical professionals stay up to date on the NEC. These courses and programs provide valuable information about the latest changes to the NEC and about best practices for electrical system design and installation. The NEC is not the only code or standard that may apply to the installation of welding equipment. Local building codes, fire codes, and OSHA regulations may also apply. It is important to consult with the local authorities and the facilities safety officer to ensure compliance with all applicable requirements. Local building codes may impose additional requirements for electrical systems, such as requirements for conduit fill, wiring methods, and grounding. Fire codes may impose additional requirements for fire protection, such as requirements for fire-resistant materials and fire suppression systems. OSHA regulations may impose additional requirements for worker safety, such as requirements for personal protective equipment and hazard communication. Compliance with all applicable codes and standards is essential to ensure the safe and reliable operation of welding equipment and to protect personnel from hazards. The principles outlined in Article 630.11b can also be applied to other types of equipment that operate on a non-continuous basis. For example, these principles can be applied to the design of electrical systems for HVAC equipment, such as air conditioners and heat pumps. The load calculation for HVAC equipment typically involves applying demand factors to the various components of the system, such as the compressor, the fan motor, and the electric heating elements. The demand factors take into account the fact that not all of the components will be operating at the maximum rated load simultaneously. By applying demand factors, it is possible to reduce the overall calculated load and to size the electrical system accordingly. The application of demand factors is a common practice in electrical engineering. It is used to design electrical systems that are both safe and efficient. By accurately estimating the actual load that will be placed on the system, it is possible to avoid oversizing the conductors, overcurrent protection devices, and other components. This can result in significant cost savings and can improve the overall efficiency of the electrical system. However, it is important to use demand factors judiciously. If the demand factors are too low, the electrical system may be undersized, which can lead to overloading and equipment failure. It is important to carefully consider the operating characteristics of the equipment and the expected usage patterns when selecting demand factors. In general, it is better to err on the side of caution and to use demand factors that are slightly higher than necessary. This will help to ensure that the electrical system is adequately sized and that it will be able to handle the expected load.